So a common question that I get is about the oxygen hemoglobin dissociation curve. And you've seen the oxygen hemoglobin dissociation curve. This is it here. It's confusing, and trying to explain it is complicated. So I'm going to give it a crack. But I'm not going to explain the curve so much as I'm going to explain the types of conditions that we might see, or the consequences of a left shift of the curve or a right shift of the curve. And hopefully that will give you some sort of practical application. So let's see how we go. So the curve relates to oxygen that's carried on the hemoglobin molecule. So think oxygen on the red blood cell and oxygen in the plasma. Now there's a relationship between those two. If I'm well oxygenated in my plasma, I'm usually well oxygenated on my red blood cell. My saturations are high, then my PaO2 is usually adequate, 80 to 100 millimeters of mercury. And that's the standard where we've got to start. Before we can understand a shift of the curve, we've got to understand what the association is, not the dissociation is. So the association is if my plasma has enough oxygen, my red blood cells are carrying enough oxygen. My hemoglobin saturation is adequate. Now, if my sats go down, my PaO2 goes down. And converse, if my PaO2 goes down, my sats will drop. And the opposite, if my sats go up, my PaO2 goes up. If my PaO2 goes up, so does my sats. So there's a direct relationship between those two. They're associated with each other. And that makes sense. You're dissolving oxygen into your blood. It makes sense that you're going to dissolve some into your plasma and carry some in your hemoglobin. Okay. Now, it's the hemoglobin-bound oxygen that does the work. So when your brain cells want some oxygen, they get it from red blood cells. They don't suck it out of the plasma. When your heart cells need oxygen, it gets it from red blood cells. The red blood cells are kind of like a postman, delivering the oxygen directly to the tissues that need that oxygen at the time that they need it. So there's a supply and demand issue. Now, when that hemoglobin has given up its oxygen to the tissues, then it drags a little bit more oxygen out of the plasma. Can you see that the reservoir for oxygen in your blood is your plasma? And that plasma contributes to hemoglobin oxygenation, keeping your hemoglobin well saturated until such time as the plasma levels drop. That too will also bring down the oxygen levels that are in your saturated hemoglobin blood. So you start to desaturate. By that time, that blood has now entered, usually into venous circulation. It makes its way back to the right heart, and the whole lot gets reoxygenated. Now, that's the normal state. So let's have a look at what influences your red blood cell to hold on to oxygen. There are two dominant influences and a minor influence that I'm going to do a different video on. But the two dominant influences for your red blood cell to hang on to oxygen is the pH of your blood, so your acidity versus your alkalinity, and the temperature of your blood. So hypothermia versus hyperpyrexia, a very, very high temperature. Now, just remember this. Blood doesn't like to pick up oxygen from the lungs if it's too hot or too acidic. So profound acidosis and hyperthermias, that's going to cause your red blood cells to say to the lungs, I see that you've got all this oxygen for me to carry, but I'm too hot and bothered to carry it. So your hemoglobin doesn't carry the oxygen. Now, it still dissolves into your plasma, but can you see that now there's not a relationship between the plasma-bound oxygen and the hemoglobin-bound oxygen? There is a dissociation. Now, what happens in that regard, this is called a rightward shift. And again, you can go back to the image and you can have a look at what that rightward shift looks like on the curve. But what it means is that hot blood and acidotic blood doesn't carry oxygen. So now it's not available to the cells. Remember, your cells need to have a relationship with the red blood cell to take the oxygen from the red blood cell. And when your blood's too hot, it's not carrying it. And when your blood is too acidotic, it's not carrying it. So states of profound acidosis will lead to tissue hypoxia. States of profound hypothermia will also lead to tissue hypoxia, because red blood cells just don't want to carry oxygen. They dissociate from it. That's a right shift of the curve. So that's the right. Now the opposite happens when you're really cold. If you're hypothermic, let's say you fell into a frozen lake. We're down in beautiful Queenstown and Southland in New Zealand, and it's cold. If I fell into this freezing cold lake down here, then I would become hypothermic very quickly. My core body temperature would start to drop, and when my core temperature starts to drop, my red blood cells bind very tightly to oxygen. I saturate very well. Likewise, if I become alkalotic, if my blood pH starts to rise and I develop alkalosis. So alkalosis in cold blood likes to hang on to oxygen, and it will transport that beautifully saturated, 100% saturated oxygen all around my body. But when it gets to the brain cells and the heart cells and the liver and the kidney and all the cells that want that oxygen, because the affinity for haemoglobin to hold on to oxygen molecules is so tight when you're cold or when you're alkalotic, then it bypasses the cells and it doesn't give up its payload. It's almost like the postman has brought the letter to your letterbox and then didn't put it in the letterbox, just drove away with the letter in his bag. So think of this. The oxygen is left on the red blood cell. It doesn't get delivered. It's left on the red blood cell. And that's called a left curve, or a leftward shift of the haemoglobin dissociation curve. There is a dissociation between the amount of oxygen that's in your plasma and on your red blood cell. Your plasma might deoxygenate, but your red blood cell hangs on to those oxygen molecules until you can bring somebody's temperature back up, or you can bring their pH back down. So that's pretty much it in a nutshell from a practical application. So have a look at your patient. How well saturated are they? And when you're looking at a saturated, oxygenated patient, you're going to simply ask the question, can I rely on those saturations to predictably tell me that this patient's going to be oxygenating their tissue? In other words, do I have somebody that's too hot or too cold? Or do I have somebody who's got a pH that's too high, alkalosis, or a pH that's too low, acidosis? Because in those states, your SATs are pretty much a random number and really don't translate to whether your tissues are being oxygenated or not. Hope that helped. It's a complicated topic, but have a look at the image again. I'm going to put it up on the screen. See ya.